Okay, can you see the slides on the screen? All right, good. Okay, so let's continue with the thermal oxidation. Yesterday we started to discuss about different factors that can affect thermal oxidation process. Okay, so the factors are temperature, ambient type, whether we run dry ox process or wet ox process, and if we also include HCl, for example, in the process, so that can also change the process. Okay, so ambient pressure in the process, substrate doping, and also substrate crystallographic orientation. And we discussed about the effect of dopant yesterday, and we talk about the differential oxidation due to different levels of doping on the wafer. Okay, we have discussed this bump in the middle, which is due to the heavy doping down there by the M+ layer. Okay, and this is due to differential oxidation, as we discussed yesterday. Differential oxidation. Right, so the next effect is substrate orientation. Okay, substrate orientation is due to the wafer orientation that we use in the growth process. And we've also discussed this yesterday while discussing about the linear and parabolic constant. Linear and parabolic constant. And we compared yesterday on the previous graph. So let's just recap on this. So if you compare the thickness of the oxide that we can grow against wafer orientation, for example, then if you put different wafers with different orientations in the same furnace at the same temperature, going through the very same settings in the process, then you'll find that at the end of the process, 111 wafer will produce the highest or the thickest oxide. Okay, and this is followed by 110, and the minimum one is the lowest one is 100, right? 100. So if you compare by orientation, 111 is the highest in terms of the oxide thickness, and 100 is the lowest for the oxide thickness. Okay, when they are subjected to the very same process condition. Kalau different, then you cannot compare. Okay, so if you compare 111 and 100 on this graph on the right, then you will be seeing this kind of trend. 111 is always higher than 100. So we've discussed before about the crystal orientation difference that causes the oxide grows faster on 111, which is due to the presence of more silicon atoms available to react with the oxidant. Okay, so 111 has more silicon atoms available if you compare to 100. So this affects oxide growth during the linear stage. Okay, so let's recall, during the linear stage, what is the limiting factor that limits the process? What is the limiting factor in the linear stage of the growth? Anyone? Apa limiting factor dia? Silicon. Okay, elaborate sikit Seri Izzian ni. Silicon, what do you mean by silicon? Yes, it is around silicon, but then elaborate a little bit. What is it about silicon? The first stage, huh, Amiro? Oxidant transport, the second stage, right? The first stage is where you haven't got any oxide yet on the silicon wafer. So what is the limiting factor in the first stage? Anyone? Sri, you can elaborate. Boleh unmute and you can write down as well. Yeah, it's around silicon, but but what is it around silicon? Yeah, interface reaction due to number of available silicon. Okay, number of available silicon atoms on the surface. So that is the limiting factor in the first stage, which is the linear stage, right? So recall this when you talk about this linear and parabolic. So recall the graph that we discussed before. E, X, ox. This is the thing, right? First stage and second stage. In the first stage, the reaction is limited by number of available silicon atoms on the surface to react with the oxidants, either it's dry or wet, okay? And in the second stage, the reaction is limited by, apa yang limit in the second stage? In the parabolic? Apa? What is the factor? What is the limiting factor in the second stage? One? Okay, oxidant transport, right? So the transport of oxidant or the diffusivity of oxidant through silicon dioxide to reach the silicon on the other side. Okay, kita dah ada barrier waktu tu, especially if the barrier is already thick, it's already growing thicker, then it's going to slow down even more because yeah, diffusion rate, because the diffusivity of the oxidants will be the limiting factor in the second stage, right? So when you talk about crystalline orientation, comparing 111 and 100, the effect will be more obvious in the linear stage because that is the stage when silicon availability on the surface will be more significant. Okay. So below you discuss factor ni, make sure you know if it's related to the linear stage or parabolic stage or regardless of both stages. Okay. So in this case, it's very related to the first one. Okay, let's have a look. Now, right, so let's compare this. For example, let's pick a process, an oxidation process. Now we are using 100 wafer. Okay, 100. So let's say we are running, okay, let's choose a wet process. Wet process, 1000 degrees Celsius. Okay, wet process, 1000 degrees C, 1 hour. What is the thickness that we get? Thickness of the oxide? Wet, 1000 degrees C for 1 hour. So what do we get from the photograph? Proper thickness, eh? So check on the graph now. 1 hour, 1000 degrees C, wet process. Does anyone write down in the chat box what's the thickness? Okay, 0.4, right? 0.4 micron, 0.4 micrometer or 400 nanometer. Okay, so that will be the Tox that we get from this process on 100 wafer. Okay, keep that in mind. Let's move on to the next one. Let's now use 100 and see, do we get a difference at all? Let's choose the same process. Let's choose the same process. 1000 degrees C. Tengok ada beza tak? Wet. I know, right? So do you have any difference at all? That's probably there. 0.2, 0.3, 0.4 basis key, yeah. 0.4, right? 2, 3, 4. 0.4. Mungkin dia punya beza dia is in the decimal of that. 400 plus 400 nano. Okay, mungkin dia punya beza ni dalam extra few nanometers. But looks similar. Okay, cuba kita tengok dry process pula. Let's try dry process. Let's see. Let's pick. Okay, let's go back to 100 and we compare. Let's pick 10. Okay, 100. Let's use 1000 degrees C. 1000 degrees C. 10 hours. Tengok bagaimana. That's about 0.2 to 0.3, I think. So let's go back to this. With the beza tak banyak, I think it's the difference in the selepas in the it's around there. So I think the difference is in the 10 nanometer. So it's not in the front side. So it's not on the 400 punya figure, but it's probably in the second number. Okay. All right, so you can compare that. So now let's look at the thermal oxide charges. So, so when you grow your silicon dioxide, so there'll be charges inside from potassium, sodium. So, and this is one of the famous issues that we have in the fab, oxide trap. Okay, oxide trap charge, which we normally say as Q. Oh, sorry. Mobile ion. Huh? We're going to discuss later on how do we solve this. But this is one of the issues that we have in oxidation process. Mobile ions. So they are all mobile ions. Mobile ionic charge. Potassium plus and sodium plus ions. Mobile. So we're going to see later on how do we solve this. Another parameter is pressure dependent. So atmospheric pressure, slow oxide growth rate, and increase in pressure, increase oxide growth rate. So higher pressure, higher P leads to higher growth rate. So as a result, we get higher thickness. Okay, so it's proportional then, proportional. So increasing pressure allows temperature to be decreased. So if you want to balance, for example, this process, we know that when you increase the pressure, you get higher oxide thickness, and then when you increase the temperature, you can also get higher oxide thickness, right? So if you want to increase one and reduce the other, you can actually balance or fix the oxide thickness. For example, if you increase the pressure of the process, so that allows you to reduce the oxidation temperature in order to maintain the same thickness. Okay, ataupun you can increase the thickness and reduce the pressure in order to maintain oxide thickness, because both contribute to higher thickness anyway. So oxide growth rate remain the same if you increase one and reduce the other. For every 10 atm, 10 atmospheric pressure, the temperature can be reduced by 30 degrees. Okay, so 10 atm. So you can actually reduce temperature of 30 degrees in order to maintain the thickness of the oxide, right? So dry thermal oxidation, pressure in oxidation tube increase. Wet oxidation, steam pressure introduced into the oxidation tube. So you can, for dry process, you can increase the pressure in the chamber, and then for the wet, you can increase the steam pressure in order to increase the pressure. So this is related to what we discussed yesterday, the B over A. Okay. So the effect is when you can see this B over A and the effect to the pressure. Okay, when you fix the B, for example, okay, the gas partial pressure is proportional to the rate of your oxide, DDT oxide. So the oxidation temperature can be reduced if the pressure is increased. So just like what we discussed now, so you can increase one and reduce the other in order to maintain the thickness. Okay. So pressure here is proportional to the rate. So pressure proportional to the rate of growth, DDT x ox. Okay. So let's look at the difference. If you run, say you run, in this case, a 100 wafers, 3 to 10 ohm cm. Oxidation duration is 1 hour. Let's say you pick one temperature, 900 degrees C, for example. So if you run at 1 ATM, then you're gonna get your thickness at about 1,000 to perhaps 2,000 or so, 2,000 kilo angstrom. 2,000 angstrom, 200 nano. Right. So on the other hand, if you run your process at 5 ATM, higher pressure, then you'll probably 6 to 7, perhaps, maybe around 700 nano. Okay. So there's a difference if you increase the pressure, and then so on and so forth. So if you want to maintain, the thickness, for example, so you can use this pressure and temperature in order to regulate your thickness. Okay. So contoh kalau you nak run, so for example, if you want to choose, say, this, okay, you ambil this thickness, fixed thickness, for example, 700 nano. So you can either run that at kalau you ada pressure in between kat sini, you can run that at this pressure, so maybe around 3 ATM maybe. So you can run that at 3 ATM 900 degrees C to be able to get that, or you can also run that at 5 ATM at 870. Okay. So that's what it means by the relationship on the previous page. Okay. You can fix the thickness by regulating your pressure or temperature. So for example, in the first case study, kita boleh run at, say, 3 ATM, low pressure, but higher temperature. Okay, 3 ATM, just to illustrate the example, 900 degrees C. So then you're going to get 700 nanometer. Okay, so that's option number 1. Option number 2, you still want to get 700 nanometer, same thickness, but you can run that at higher pressure, 5 ATM, but lower temperature. You just ambil satu horizontal line ni, then you extrapolate accordingly. So that's probably 870. Okay, so you can run that at 3 ATM 900 degrees C or 5 ATM 870 degrees C to be able to come to the same thickness, right? So paham ke tu? Can you see that? right? It's clear, right? It's very simple. Just see what is your target thickness, 700 ke, 1000 ke, whatever thickness that you want, and then you can just see where can you get that from, right? In terms of the pressure and temperature, because anyway, both pressure and temperature contribute to the oxide growth rate with proportional relationship. Okay, so kalau you increase satu, reduce satu, you akan dapat same thickness. Ataupun kalau you increase dua-dua, of course you akan dapat higher thickness lah. So the graph on the right is the difference between 111 versus 100 at any temperature, for example. So look at the difference now in terms of, but let's look at the difference here. Say if you run, let's pick one. Steam pressure, what x-axis is the steam pressure, y-axis is the thickness. So let's pick at these perhaps 10. Lebih kurang ni. Then you're running at 920. Tak apa jelas tu. So let's look at the difference here. It's very small. Say 0.1. Yeah. So the difference is very small. 5 micron to 4 something, I think. Okay, just a very small difference between the two wafers at the same setting, right? So that's 1.1, 0.02, 0.03, 4, 5, 6. Oh, ni kat atas Yeah, if you look at this one, nampak very small difference. But 1 is higher than 100. Right, another factor is if you add chlorine to the oxidants, right? Chlorine can be in the form of anhydrous chloride, Cl2, anhydrous HCl, can be TCE, can be TCA, right? So the point is to increase the oxide growth rate. So this species is also proportional to the growth rate. DDT lah, growth rate lah. Oxide, right? Oxide cleaner, so it will clean the oxide from the mobile charges and to improve the device performance. So let's see how does it work. So introduction of halogen species, the TCA, TCl, anhydrous, all the stuff is now during oxidation, usually with this much, 1 to 5% of HCl or TCE to the oxide. So it results in reduction of metallic contamination, right? So we talk about the mobile ions. So it will reduce the metallic contamination. And then, so basically it will clean oxide from charges, from mobile charges. Mobile charges. K plus and an A, right? So note that this sodium and potassium ions are mobile. Okay, and this is very dangerous. So you can, for example, if you have these mobile ions, but ion acting with the chlorine species added to the oxidation process, so it will be trapped as a compound, MCl. Okay. Your whatever ions acting with the chlorine species to trap, then they will be trapped, no longer mobile. Okay. So another process, this is not the, this is no longer the factors. This is another subtopic in this topic, in this oxidation topic. So it's called low-cost process. So it's a form of process that you can do in order to grow oxide. You can grow oxide in the form of this. Contoh on silicon, you want to get this oxide on silicon eventually, and to get this, you need to use low-cost process. So what is low-cost process? So it's a process where we have about 100 angstrom of silicon dioxide, pad oxide, we call it pad oxide, to release mechanical stress between nitride and silicon. So kita tengok, so what's actually happening is we have to, okay, you started off with your silicon wafer, bare silicon, then you grow your oxide on the silicon. So oxide is the green color on the silicon, and then you have your nitride, right? Nitride and polysilicon there on the sides. Then at the moment you've got this, structure, this is your starting structure. Then with this structure, you then you redo the oxidation. You masukkan sampel ni dalam oxide furnace, and then continue the oxidation, and you're gonna get this kind of growth. Kedua ni, you're gonna get your oxide to be thicker on the central part, and then oxide on the sides will be grown as well, but it's not as thick as the central part. Okay, then you can due to the stress on the sides, this nitride will then be peeled off. Okay, dia akan terkeluar, then you're gonna get your your oxide like this. So ini kita guna untuk pad oxide. So you're gonna see later on where do we get this, right? Kena buat etching juga in between before you get that silicon nitride etch. So this is combining a few processes at once, but later we're gonna see how do you etch nitride and stuff in the next process. So it's called low-cost process. So another illustration of the low-cost process. So you have your oxide grown on silicon. So this is your structure, this is your wafer, and then this is your oxide. Okay, then you have your nitride deposited. Then your oxide will grow thicker in the central part and then slightly thinner on the sides and peel off, and you're going to get the structure. Right, another issue when we talk about thermal oxidation is called dopant redistribution. Dopant redistribution means the dopant will be redistributed in terms of its profile as a result of oxidation process. Okay. Why do you think, let's just guess, why do you think the dopant will be redistributed during oxidation process? Redistributed. Kenapa dopant ada redistribution during the oxidation process? What makes them to be redistributed? Okay, for equilibrium, all right. But what drives them to be redistributed? Kenapa ada redistribution in the first place? What is the driving factor during oxidation? Any guess? Kenapa can't we just have no distribution? Apa menyebabkan dia redistributed? Agak-agak during oxidation process. What is so unique about oxidation process sampai dia redistributed? Okay, different concentration lagi. What forces them to be redistributed? Lagi, siapa lagi ada answers? You can just write down. Dopant redistribution. apa driving force dalam proses tu? Kenapa dia tiba-tiba ada redistribution pula kan? What is the main parameter that could drive this redistribution? Anyone? Tulis je kat situ, saya tengok. In etc. Buka buku ni. Depletion layer, okay. Any other answers? Impurity redistribution, page 50. Ini kalau buku Gary on page 50 ya. Anyone? Tulis je, okay. We discuss. Kenapa ada redistribution? Tadi jawapan tadi siapa cakap ni? Haziq kan? For equilibrium is the result is the result of the redistribution. So dia akan eventually redistributed sampai dia capai equilibrium. Tapi sebelum redistribution itu terjadi, what is the main factor forcing the redistribution? Relate back to the typical condition, typical process parameters of thermal oxidation. What is so special? Kenapa dia? Yes, that's the thing. Okay, temperature, right? Temperature yang force dia to be redistributed. So do we run oxidation? Typically, do we run oxidation at low temperatures or high temperatures? Typically, low or high temperature. Kita dah discuss dulu ni, tengok chart banyak kali lah kan. Tengok dia punya rate and everything. So are we talking about high temperature region or low temperature region when we talk about oxidation? Typically high, right? So bila high, bila kita describe, we have been talking about 900, 1000, 800. We hardly talk about 200, 300, even though oxidation pun boleh dapat juga at 200, 300, but then the rate will be very, very low. Okay, but we have been discussing about high temperature region. So bila you ada high temperature punya setting, so that will be the force, the driving force for the impurities or dopants in this case to be redistributed. Okay. So that's a driving force. Kalau low temperature is slow lah. We have learned about diffusivity last time in 3 and 6. I think we discussed about when we talk about passivation or trap states, Shockley Reed Hall recombination, SRH. We talk about defects. We talk about if you incorporate metals, for example, into the silicon material or device, then it's going to end up as a shallow state kan? Ingat kita shallow state no? Trap state. ECEV, we have shallow trap, right? Shallow. You also have deep level defects, right? Deep level, DL actually, deep level defects, where the electronic states yang saya tulis draw ni is the electronic states dalam band gap. So we've been learning that in the band gap, there's not supposed to be any electronic states, but the forbidden gap kan to begin with. So it's just EC then EV. Tapi kalau ada some state in between tu, generally it'll be deleterious to the device. It'll be very bad to the device. So even worse if you have trap state too close to the mid gap, right? We talk about mid gap, which is close to EG/2. So dia akan suck all your carriers daripada device by recombination, okay? And this will be worse. And katalah you ada metal on your silicon wafer, and then just imagine kalau you ada metals on the surface, then it probably can wash off the metals. Tapi kalau metal tu dah ada kat surface, and then the next step is about high temperature. then whatever metals that you have on the surface will be driven into silicon, will be diffused into silicon. They can migrate dalam silicon dan disrupt the lattice physically, and electronically it will be this. Okay, it will be represented as trap states in the device. So that's driven by high temperature. Kalau you run low temperature, mungkin the effect is not that bad. But if you drive the metals through high temperature processes, then they akan diffuse lagi laju, because diffusivity is related to the temperature. So coming back to this, dopant redistribution is driven by high temperature. Okay, and when we talk about thermal oxidation, we're talking about high temperature process. Even though you can also have your oxide at low temperatures, you can even have your oxide grown at on the bench, native oxide. Kan kita discuss tentang 3 nanometer, 4 nanometer of native oxide is also possible. But generally, when we talk about furnace process, then we're normally talking about 800 and above degrees C. Right. So dopant redistribution, you can see now the top graph. So it's showing the dopant profile in the oxide and in the silicon. So this is essentially like that. Dia macam, so it's actually your wafer, silicon oxide on, you flip bagi 90 degrees anti-clockwise, then dia akan dapat vertical. So this is the top area of your oxide on silicon. Bottom. So the same goes here as well. Okay. So dopant redistribution is given by M. It's calculated by M equals to C1 over C2. And that is equilibrium concentration of impurities in silicon do atas, over equilibrium concentration of impurities in SiO2. Silicon over silicon dioxide, right? So in order to get this, you have to look at the interface between both, right? So if your equilibrium concentration at the interface, equilibrium concentration of the impurities here are dopants. So we talk about this in 386 as well, where we talk about desired impurities and undesired impurities. So dopants are desired impurities, right? And metals are non-desired impurities. So dopants buat kita masukkan dia dalam lattice. So we want to do that, right? We do it on purpose, but unfortunately, it's going to suffer from redistribution during the process that we have to manage. So if you look at the first case on the left, so M is more than 1 because the equilibrium concentration of dopants in silicon at the interface is higher than in oxide, right? So that's why high over low, then you get more than 1. So, okay. So on the other hand, on the right, the dopant concentration in silicon at the interface is lower than the concentration in the oxide. So that's why you get M less than 1. So that's given by C1 over C2. So silicon atas, numerator will be silicon, denominator will be oxide. So dopant redistribution, dopants affect device performance. The change in dopant location and concentration, during oxidation can affect device operation. So just imagine if you have already diffused certain depth and certain concentration of dopants, phosphorus or boron, on your device, and suddenly the samples or the wafers go through thermal oxidation at high temperature, then your dopants will be redistributed, and then your intended properties of the junction, for example, will not be exactly the same as what you designed due to the redistribution during the thermal oxidation. So bila you design you punya thermal oxidation process, and the dopants diffusion, we're going to look into diffusion later on. So you can take this into account. So you design is one, and then you diffuse to form certain characteristic of the junction, and then you have to also incorporate the effects of the dopant redistribution during thermal oxidation that could change the properties of the junction, either a lot or little. Okay, but you have to know the effect before and after, right? Then only you can tell the performance of device operation. N-type dopants move deeper into silicon. N-type dopants like phosphorus, arsenic, antimony move deeper into silicon, so high concentration at the silicon dioxide interface. So N-type move deeper into silicon, so you'll probably find higher concentration of the dopants in the silicon rather than in the oxide. Okay, so that'll probably give you, yeah, that should give you M more than 1. On the other hand, P-type dopants move into silicon, move deeper. Okay, you have to look at this. P-type dopant move into silicon dioxide. P-type dopant, on the other hand, move into silicon dioxide and deplete the silicon layer. Right, this is the natural tendency of the dopants. So, do you expect in the second case M to be less than 1 or more than 1? Second case, dopants, P-type dopants move into silicon dioxide and deplete ni kurangkan dopant daripada silicon. So, do we expect in this case M to be less than 1 or more than 1? Anyone? You know, less than 1? Ada lagi jawapan lain? Remember, C1 over C2 is a concentration of dopant in silicon over silicon dioxide, right? So in this case, since dopants are moving into silicon dioxide, so you should expect silicon dioxide to have more, and silicon will be more depleted. So less over more will be less than 1, right? So it should be less than 1 then. Tengok, P-type, N-type dopants, you're going to have, yep, that's less than 1. So N-type is going to move into silicon. So the tendency is to be more than 1 for N-type. Then for P-type dopants, the dopants are going into the silicon dioxide, deplete silicon layer, and therefore M less than 1. Right. So let's have a look at this. Case 1, oxidation of boron dope silicon. A boron dope silicon oxidation process. So it is a P-type silicon boron dope. M dia bagi 0.3. So look at C1 over C2. So this is the interface. M C1 over C2. C1 is clearly less than C2, isn't it? So say, contoh saya ambil number yang, so that's probably 3 over 10, something like that, right? Silicon over silicon dioxide, so that will give you about 0.3. So ni imaginary number, yeah, based on the scale there. So that's probably 3 over 10. So boron will be depleted near silicon dioxide interface. So that's what it means. And boron is P-type, right? P-type and P-type, remember we talked on the previous page. So dopants are moving into silicon dioxide and deplete silicon layer. So they can migrate from there to there. Boron. Right, so leading to M less than 1. More dopants into silicon and more dopants into silicon dioxide and less dopant left in the silicon due to depletion. So let's look at another case, case number 2. Oxidation of silicon dope with phosphorus. N-type silicon, N-type. So then we run oxidation. Then you see again, MC1 over C2. Silicon is higher than oxide. So that's probably 10 over 5, contoh ya. Okay, so therefore M is more than 1. So dopant piling up near silicon interface. So in this case, phosphorus, contohnya, migrating into silicon, piling up near silicon interface for the N-type dopants. So leading to M to be more than 1, right? So ini pun sama, you can have a look later on. For the case of boron, boron is hydrogen, phosphorus, gallium. Okay. So we're almost done. Good. Right. Polycrystalline silicon oxidation. So we have been discussing about monocrystalline silicon oxidation process. So what if we run a polycrystalline silicon thermal oxidation, right? So we know that polycrystalline has multiple grains, and each grain, so you can have a look here. So these are all one grain. So this say 100. The next grain is probably 111. This grain is perhaps 101. And this is again perhaps 100. This is 111. Yeah, right. So you can in any sort of combination depending on the growth process. So, and we learned that when you talk about the growth rate or the thickness oxide against orientation, we know that 111 is the highest, followed by 101, followed by 100, right? In terms of the oxide thickness for different crystalline orientation in the same thermal oxidation process. So as a result, we're going to get a different growth rate throughout the polycrystalline silicon. So you're going to grow oxide outside, so they can react with silicon, just like what we learned in the growth model. So due to this different growth rate, we're going to get a very rough oxide across, okay, encapsulating the silicon. Sebab dalam ni silicon dia polycrystalline. So growth rate dekat sini is different from sini, is different from sini, depending on the crystalline orientation, of course. So due to this random nature of the polycrystalline, so you're going to get quite a rough oxide thickness across. Okay. Kalau mono, then you're going to get a very smooth because it is just a single crystalline orientation, and the rate is only single. The growth rate is only single due to single orientation. But due to this, you have plenty of different orientations everywhere randomly. So as a result, we're going to get a rough oxide thickness across. Overall growth rate is higher than single crystal due to the mixture of different composition, different orientations. If you compare this to, if you compare oxide, for single crystal, say, katalah 100, then that will be the lowest if you compare to the mixture of polycrystals. So ada 101, 100, right? Okay, now you have got your oxide done. So this is your silicon. So essentially what you're going to have is something like this, raw after the process, silicon dioxide, cleaning. But then we're going to do some cleaning, and we're going to use the top oxide for the next process. So kita akan remove. So you're going to remove this on the side. You're going to remove this on the side. You're going to remove the oxide at the back as well. So they're all gone, leaving just the top surface as the active region. Remember, go back to the active region. When we talk about device fabrication, kita nak pakai atas ya, atas surface ya. So everything will build just on the surface, nothing within the bulk. Okay. Kalau on the other hand, we learned last time in 386 about solar cell, for example. Solar cell kita nak pakai dalam bak. Okay, sebab kita nak absorb light dekat everywhere dalam silicon, and then electron hole pair will be migrated to both sides. Electron will be going into n-type, hole will be going into p-type. So you're going to use the whole vertical structure dalam silicon for solar cell. But for this MOSFET, kita punya active layer dia kat atas, active device, active region kat atas. So that's why we can use other areas kat belakang ataupun at tepi untuk gather. Remember last time we talked about gathering, untuk kumpul all the defects which will then be removed. Sebab kita ada non-active areas outside of the front region. Tapi kalau solar cell, kita akan pakai the whole region. There's no passive area, semua active. Okay, so that's why when we talk about different devices, then the requirements on the material, the requirements on the devices will be different. Okay, so the clearest one is the difference between MOSFET to solar cell as far as the design is concerned. So kita akan will be left with oxide on the silicon for the next process. Okay, so bila kita dah ada oxide on silicon, so there'll be few characterizations that we have to do. So go back to wafer characterization, but in this case, it's not wafer characterization, but rather oxide characterization. So normally in the fab, we call this all this kind of measurement as metrology. Kalau you jumpa online metrology engineer, that means the job has something to do with the measurement of something, characterizing something. So in this case, if you talk about oxide process, then we want to inspect the surface of the wafer. If you go back to the wafer, tengok wafer dekat atas, top view, kita ada notch. Macam biasa kita discuss last time. So you want to make sure that the particles are not there, or the particles are within control or within specs. Kalau 5, then 5 saja. Kalau 1000, then 1000 lah. So depending on the sensitivity of the device, then, right? So surface inspection. So you want to make sure that the oxide doesn't introduce unnecessary particles or unwanted particles on the surface that will affect the next process. Okay, kita akan tengok kenapa dia akan affect the next process. Let me finish in like 2 minutes. If you look at this cross section, you ambil wafer ni, tengok dari side, dari tepi. If you have particles, it'll probably be something like that, dome ataupun besar ke, saya exaggerate just to show you particles. Then if you have these particles, carry it to the next process. Next process is lithography. Okay, so we're going to use light to be focused to print your circuit structures, your circuit yang kita dah design dalam reticle, dalam mask, dalam circuit design engineer dah buat. Kita nak print circuit tu dekat wafer through photolithography process or printing by light. So what happens if you want to print structures on a very dirty wafer? So, maknanya you punya wafer tu ada macam-macam. Macam mana nak print? Takkan you punya circuit tu nak print sengit tu kan? Ataupun dia punya, nanti you going to learn about focus. So kalau you jenis yang minat kamera ataupun jenis yang suka main fokus and edit gambar, then probably you can appreciate the next topic more, right? Because it's all about focus, getting good images. So, macam nak dapat gambar, you kena tekan dekat screen kat tengah tu nak dapat focus and everything, right? If it's not in autofocus mode. And then the same goes to lithography. Kalau you nak tangkap gambar tapi you don't focus, and then you have on a paper ataupun atas satu gambar you ada something, ada particle ke ataupun something drop kan, that will be out of focus to some extent. Sebab dia macam confused. Nak fokus kat area mana kan, gambar ke ataupun particle kat atas gambar tu, right? So the same thing happens, or the same thing will be discussed in lithography. Kalau you ada particle, then it will be out of focus, then you cannot print your features, you cannot print your structures well, and that will be ending up as defects. So nanti you akan tengok features yang kita nak print tu yang tegak akan jadi sengit, akan jadi broken, akan jadi collapse due to out of focus punya issue, right? So that's why you have to make sure that the metrology is done properly. So surface inspection is done to make sure that the surface is clean and ready for the next process. And you want to also verify the oxide thickness to make sure that you get what you intend to get. So if you're targeting for 10 nanometer, then you should make sure that it's 10 nanometer across. So to be able to get the measurement done, you might want to do characterization at multiple points. Tak boleh buat single point, single point won't tell you much. So ada banyak resipi dekat metrology. Again, recipe. You ada banyak recipe at metrology. Some recipe will be measuring 5 points. Some recipe will be measuring 9 points on the wafer. Some recipe will be measuring perhaps 25 points, 50 points, 100 points. So kalau you measure lagi banyak point, so it's going to consume more and more time, but you're going to get more and more accurate data if you compare to just 5 points, or the worst one, 1 point or 1 point tak boleh lah. Right? So the more you measure, the more accurate result you get, but then it will affect the throughput of the process. Throughput. Throughput ni wafers per hour. Berapa wafer per hour yang you can measure? Berapa wafer per hour yang you can oxidize? Berapa wafer per hour that you can print? Berapa wafer per hour you can diffuse? Right? So semua proses we'll be talking about throughput. Right? Manufacturing team, this is the bread and butter of manufacturing engineers. Right? Every day it's all about throughput. Kalau throughput drop, they have to justify why is it dropping. Equipment down, process shutdown, particle problem, all the stuff. Right? So oxide thickness, and finally oxide cleanliness. Remember the HCl incorporation to capture the mobile charges to make sure that they are immobile and then eventually removed from the oxide to make sure that it's performing well as an insulator on the device, right? So yeah, then after you've done your metrology, then the wafers will be ready for the next process, which is photolithography. Right, so is it clear so far? Thermal oxidation? We're done with thermal oxidation. Is it okay? So kalau you perasan, kita akan dalam fab proses ni kita akan discuss the process and then the metrology. Process, metrology. Kemudian next process, next metrology. Next process, next metrology. So you can deposit, you can glue oxide, you can measure, you can characterize. Then you go to lithography, you got to measure, characterize. You go to etch, measure, characterize. But the characterization and the processing will be different from process to process. But the whole idea is whatever you fabricate, whatever you deposit, whatever you grow, has to be characterized, has to be understood before it goes to the next process, right? That's all. 12 already. Clear? Oxidation, we're done, okay? Lepas ni no more oxidation until we discuss about the whole process flow. Lepas ni kita akan guna oxide yang kita dah grow to do lithography. Then guna lithography circuit yang kita dah print in lithography for etching. Kemudian kita akan guna for the next. It will carry structure yang kita ada sekarang, it will carry into the next process and so on and so forth. Okay, tak ada soalan All good? Semua clear? Semua faham? Yeah? Right, so I'll see you then on Friday. Oh, okay, hold on. Friday. Kita 2 jam kan? Friday, we'll have a class, of course. But the time I will need to tell you because I will have to do a presentation at Mosti online at 9 AM. So just in case kalau saya terhabis lambat, you just wait first, okay? So saya ada presentation. By right, it should be done within 1 hour, right? It's just a 30-minute presentation for new grant, for new project. And supposed to be 30 minutes of Q&A max. So that should be done by 10. So just in case kalau saya tak appear online by 10, we just tunggu sekejap. But I don't think it's going to take long. But just in case kalau terlajak tu, saya belum online means saya belum habis right? It's going to be on different platforms. So you just wait anyway. Ataupun kita tengok nanti kalau saya sempat reply dekat WhatsApp, then we're going to discuss in WhatsApp. Kalau you nampak saya tak reply apa tu, mungkin saya tak habis lagi lah. So give me like, say, 10 to 15, just in case. Kalau habis awal, then kita proceed as usual lah, 10 AM proceed. Kalau you nampak saya tak ada, then maybe I'm not done yet, right? So I'll see you Friday then, insyaAllah. Bye-bye. Assalamualaikum.